Hi, I'm Vaughn Winchell from Howard Community College. This is a video for students in my Calculus 1 class on the quotient rule for derivatives. Before we dive into this, I want to remind you that quotient is a math word that means the answer to a division problem. Fractions are a type of division, so very often when we use the quotient rule, we're going to use it on problems that look like fractions. Okay, let's dive into this. I have here a thought experiment similar to the one that I did with the product rule, but in the interest of not being too wordy, I'm going to kind of fly through this. Suppose I have two functions, t of x and b of x. And t of x is x to the fifth, and b of x is x squared. I'll tell you here that the t stands for top and the b stands for bottom. Because I said here that my function f of x is t of x over b of x, the top over the bottom, that is x to the fifth over x to the second, which equals x to the third. So which of the following choices A, B, C, or D is equal to f prime of x? Now, I was able to simplify this fraction, right? F of x is x fifth over x squared. That makes f of x x to the third. So I know that the derivative of x to the third should be 3x to the second. But I have some choices for how I might do a quotient rule if the fraction was hard to simplify. If the fraction was, for example, sine of x over x squared plus 5. That's not a division I can do easily. Or x to the third plus 1 divided by the natural log of x. That's not a division I can do easily. So I need a rule that will let me do derivatives for fractions when I can't simplify them. So is it choice A, derivative of the top over derivative of the bottom? Well, that would be 5x to the fourth over 2x, which would simplify to 5x to the third over 2, and that is not the same as 3x squared. That must not be how the quotient rule works. I tried some complicated things, B and C. They didn't work out. B and C are two parts of what the eventual quotient rule turns out to be. It turns out to be this thing at the bottom, this very complicated rule that f prime of x, the derivative of a quotient, is the derivative of the top times the bottom minus the top times the derivative of the bottom over the square of the bottom. Oh my God, that's so hard. I have a memory trick for this. But before I get to that, I want to get to the slide where I show you the rule, which has, like with the product rule, in that blue box, the whole thing written out in symbols. I don't remember this rule. I've told you before, I teach calculus, but I don't think of myself as a mathematician. I think of myself as a math teacher, a math explainer. Since I first learned this rule in about 1980, I've been carrying it around in my head this way. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the square of the denominator. That's a mouthful. And also the thing I want to point out to you in the slide where I've written this out myself is this minus in red type here, right? There's subtraction in the numerator of the quotient. Subtraction is not commutative. With subtraction, the order matters, and if you change the order of the minuend and the subtrahend, if you change the order of the two numbers, you're going to change your answer, right? 10 minus 3 is 7, but 3 minus 10 is negative 7. Okay, so if f of x is the result of dividing two smaller functions, then f prime of x is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the square of the denominator. That's how I've been carrying it around in my head for more than 40 years because I'm very old. On the next slide, I'm going to tell you a little story. I've mentioned Dr. Loretta Tacoli before. When I took Calculus 1 here at HCC a long time ago, she was my professor. And we worked together for a lot of years until she eventually retired. She had a different way of remembering this quotient. And she told us this mnemonic. A mnemonic is a memory trick. She told us this mnemonic in class. And when she told us this mnemonic, I remember sitting in class and thinking, oh my God, that is the single most humiliating thing I've ever heard an adult person say voluntarily. I will never say that out loud and publicly. I thought it was absolutely stupid and humiliating. And some years later, my own daughter was taking a business calculus class and she needed to know the quotient rule. And I said to her, well, I have this memory trick. It's really embarrassing, but I'll tell you. And she said, wow, that's awesome. I can remember that. You need to teach this mnemonic to everybody you teach from now on. So because my daughter Sarah said I have to teach you this, here we go. Here's how this mnemonic, this memory trick works. Let's call the numerator of the fraction high, which makes sense because we write it up top. It's high. And we're going to call the denominator ho. Ho sounds like low, but if you say ho instead of low, this thing just sounds more ridiculous and therefore easier to remember. All right, second bullet point. If I want to say the derivative of the numerator, instead of saying high, I'm going to say d high, derivative of the high. If I want to say the derivative of the denominator, I'm going to say d ho, the derivative of the bottom, right? So I can think of the quotient rule this way, and I swear on a stack of Bibles, this is the way Professor Tacoli told us this, with the intonation and everything. The derivative is ho-de high minus high-de ho over ho-ho. Why do we say ho-ho instead of ho squared? Because it sounds stupider if you say ho-ho. And I think the thing that makes this memorable is that it sounds so ridiculous. Ho-de high minus high-de ho over ho-ho. I'm never going to say that in public. Well, here I am, humiliating myself for your benefit because I care. Okay, ho-de high minus high-de ho over ho-ho, that's the thing we have to remember. By the test, we need to know this. Let's look at an example. So here I need to apply the quotient. It says use the quotient rule to find the derivative of k of x equals 5x to the second over 4x plus 3. I could do some polynomial long division. I could try to get this as a quotient. It doesn't divide nicely, right? So if I'm going to find the derivative, here's what I'm going to do on the next slide. Here's my function. I have the numerator high written in red. I have the denominator ho written in blue. K of x is 5x squared over 4x plus 3. So k prime of x is ho-de high. That's 4x plus 3 times the derivative of 5x squared minus high-de ho. My prime didn't come out up high the way I would have liked it, but 5x squared times 4x plus 3, the derivative of that, over the square of the denominator. So I take this 4x plus 3 and I square it. And I have a little note here on the side. I know how to do 4x plus 3 times 4x plus 3. I can do it in my head. It's going to be 16x squared plus 24x plus 9. But I'm going to tell you that I've been doing calculus on and off since 1980. That's what, like 112 years. And in that time, I have never once seen a problem where there was any benefit to multiplying out the square of the denominator. Just don't do it. Theoretically, maybe the numerator might work out so that you could cancel something between the numerator and the denominator, but if you were going to do that, you'd want the denominator in factored form, not multiplied out in polynomial form. And if it doesn't cancel, then having it as a polynomial is no better than having it in factored form anyway. Just, I'm telling you, nothing good will come of multiplying out the denominator, so I'm not going to do it. But I am going to simplify the numerator. Okay, so in the numerator, I have 4x plus 3 times 10x. So in the third line, that makes 4x to the second plus 30x. minus, then I have 5x squared times 4, that's 20x squared. The denominator I'm leaving is 4x plus 3, quantity squared. Tidy up the numerator a little more, combine the quadratic terms, the x squared terms. I have 20x squared plus 30x over 4x plus 3, quantity squared. In the numerator, it's true that I could factor out 10x to the first. I could call the numerator 10x times the quantity, 2x plus 3, but the 2x plus 3 doesn't cancel with the denominator. So there's no benefit to doing it, and that's why I'm leaving it like this. I have some examples that I want to talk about, but I'm going to save them for class. And I would like to see you in the next video where I start to talk about section 320.